Okay, so we were discussing acid-base equilibria and or titrations a little more specifically, and we looked at weak acid, strong base titrations, and we know that when a weak acid like acetic acid, when it is at the equivalence point, you can imagine that the acetate ion is present. Weak acid dissociates into acetate ion, acetic acid dissociates into acetate ion and H plus. So acetate ion which is present is the anion of a weak acid, right? And we learned in the previous chapter that anions from weak acids will act as bases. So we would expect the pH to be above 7 at the equivalence points. Theoretically, when the equivalence at the equivalence points, when the acid completely neutralizes the base, pH should be 7. It should be only water and a salt. There should not be any acidicity or basicity. But when it comes to the weak acid, since the bases, the anions are going to act as a base, the pH would be above 7. Now we looked at the sample exercise 17.7, calculating pH for a weak acid strong base titration. If you want to look at that calculation one more time, let's look at it before we do the practice exercise. So here the question is, calculate the pH of a solution formed when 45 milliliters of 0.1 molar NaOH, which is a strong base, added to 50 milliliters of 0.1 molar acetic acid, which is the weak acid. Now, first goal is to calculate the concentrations of acetic acid and NaOH using the number of moles and, molarity and volume. Not that when we do the titrations, even though you start with a particular volume, after some time you keep adding things into it, the solution's volume is going to change, right? And concentration is usually expressed as moles per liter of the solution. So if the volume is changing, the concentration is going to change. The only thing remain constant is moles of the substance, right? Moles will not change, but molarity will change. So you will use the acetic acid volume and its molarity to calculate moles of acetic acid, and then NaOH volume and molarity to calculate moles of NaOH. Then, just like we have been doing before in the equilibrium calculations, create the table. We have before the addition 5 into 10 to the power negative 3 moles of acetic acid, no OH, no acetate or no water. And we are adding 4.5 into 10 to the power negative 3 moles of OH minus. If you look at the reaction, they are 1:1 mole ratio. So every mole of OH minus you add 1 mole of acetic acid will get used up, right? So the change in acetic acid concentration will be negative whatever the amount of OH minus. That is why after the addition you are left with only 0.5 into 10 to the power negative 3 moles of acetic acid, because 4.5 into 10 to the power negative 3 is being used up. So what happens to that used up acetic acid? It turns into acetate ion. That is what the other way of saying acetic acid is used up. So the acetate ion, initially you didn't have any, but after the addition of this NaOH, the concentration of acetate ion is 4.5 into 10 to the power negative 3 moles. Now, not that these are all given in moles, right? Because we converted into number of moles. Now, after this titration, you can imagine you had 50 ml of something, you added 45 milliliters to it, the total volume is now 95 milliliters. So the molarity, when it comes to molarity, it would definitely change. We cannot just say, oh, 0.5 into 10 to the power negative 3 moles is 0.5 into 10 to the power negative 3 molarity. It will change. So you again using moles per liter expression for molarity. Now finally express everything into the Ka expression. And you know the value of Ka for acetic acid, 1.8 into 10 to the power negative 5. So we know everything except the H plus concentration in the expression. So solve for H plus, and once you get H plus, you can calculate the pH, negative log of H plus. So that's the philosophy you use for calculating pH of a weak acid base titration. Now let's look at the practice exercise and solve it. So calculate the pH in the solution formed by adding 10 milliliters of 0.05 molar NaOH to 40 milliliters of 0.025 molar benzoic acid, and Ka is given to us. Then the same question has a part B also. Let's do the first part. So first step is, it's exactly like the previous problem or the sample exercise. So the first step is, using the molarity and the volume, calculate the number of moles of each substance you have initially. So okay, so we have 10 milliliters of 0.05 molar NaOH. So moles of NaOH would be, how do we calculate that? What is the molarity? Oh, the book is too far away. Oops, wait a second, let me get settled, guys. So the molarity is 0.05. So 0.05 moles per liter multiplied by, what is the volume of NaOH? 10 milliliters, which is 0.01 liters. So what is the number of moles of NaOH? Please calculate that. Then the next step would be similarly calculate moles of benzoic acid, which is C6H5COOH. C6H5COOH. Again, molarity of benzoic acid is 0.025 moles per liter multiplied by, what's the volume? 40 milliliters. Oh, so 40 milliliters is 0.04 liters. Again, liters and liters goes away. So what are the number of moles? Moles of NaOH is 5 into 10 to the power negative 4. That is the number of moles. And how about benzoic acid? .001 moles. Okay, so we have the initial moles. Now let's write the reaction and make the table so that things are clear. So the reaction is going to be C6H5COOH, which is our weak acid, and we are adding the strong base, so it is completely ionized, so we are worried about only the OH minus from NaOH. And what are we making? The benzoate ion, C6H5COO minus, and water, just like the acetic acid, right? Okay, now let's write the numbers we have. So initial, or before we have, what is the number of moles of, okay, 0.001 moles of benzoic acid. We have no OH, no acetate ion. Then we are going to add NaOH now. You start the titration. You are adding the number of moles of NaOH. 5 into 10 to the power negative 4 moles of NaOH is added. And after the addition, so this is what you had initially. Again, here the mole ratio is 1 to 1. So if you add 5 into 10 to the power negative 4 moles of OH minus, 5 into 10 to the power negative 4 moles of benzoic acid will be used up, right? So what is left? How much benzoic acid is left? 0.001 minus 5 into 10 to the power negative 4. What do you get? What is left also the same number? Okay. It is? Okay. So 5 into 10 to the power negative 4 moles of benzoic acid is left. All OH is used up, so we don't have any OH left. Now, how much acetate ion has formed? 5 into 10 to the power negative 4, because again for every 1 mole of OH minus reacted, 1 mole of acetate ion is formed. So we have 5 into 10 to the power negative 4 moles of acetate ion formed. Now, are we given the Ka? Yes, we are given the Ka. So now we can write the equilibrium expression. So the benzoate ion, what will be the dissociation if you write the benzoate ion? C6H5COO minus dissociating to C6H5COOH and I didn't include water. I'm sorry. You need water here, right? Now wait a second. I'm writing it the opposite way, guys. The acid dissociation, that's what we are writing, right? So benzoic acid dissociating to benzoate and H plus. This is the acid dissociation, and Ka is given to us. Ka is 6.3 into 10 to the power negative 5. Now you can write the or plug in the numbers for the Ka expression, right? Ka expression would be, what are the products? C6H5COO minus multiplied by H plus over C6H5COOH concentration. This would be your Ka expression. Now let's substitute the numbers. What do we know? Do we know the C6H5COO minus concentration? Right here. 5 into 10 to the power negative 4 multiplied by, we don't know H plus concentration because this table doesn't contain an H plus, right? So we will represent H plus as just H plus, because that is what we are going to solve for, divided by C6H5COOH concentration is also the same. So 5 into 10 to the power negative 4, which is equal to 6.3 into 10 to the power negative 5. Now since these two numbers are exactly the same, I guess they cancel out. So basically H plus is the same as Ka. So what is the pH? Negative log of 6.3 into 10 to the power negative 5. What should be that? Let's check whether we get the answer in the book. That's right. Well, you checked. Why would I plug in the numbers too? So when you take the negative log of Ka, you will get 4.2. So the pH of that solution would be 4.2. So review the concept one more time. First, this is the only stuff given to you along with the Ka. Okay? So using the molarity and the initial volumes given, convert the both species into number of moles, then create the table for the reaction. You are adding base to the acid, so write out the reaction and put the number of moles in its appropriate places. You have initially, the moles of acid, and assume that no base is added, that is the initial state, then addition of base, and after the addition of base, what happens? This comes from the mole ratio. So 1 mole of acid reacts with 1 mole of base means for every mole of base you added, 1 mole of acid is used up. So find the difference between those two numbers. You will get the number of moles after. And the weak anion is formed exactly in the same proportion. Then the Ka is given means you have to write the equation of the dissociation of that weak acid. Not that this equation is different from the titration equation. Titration is acid and base, but Ka equation is just the dissociation of the weak acid. Then substitute the numbers. The only thing missing would be the H plus. So solve for H plus and you will have pH from the H plus concentration. Okay, what is the second part of this question? Calculate the pH in the solution formed by adding 10 milliliters of 0.1 molar HCl to 20 milliliters of 0.1 molar NH3. Okay, now we have a different setup here. Here what we have is a weak base, ammonia, and we are adding a strong acid. What do you expect the pH to be? 7, above 7, below 7? What? Why above 7? That was with the acetic acid, a weak acid titrating with a strong base. Here the case is opposite. Now look at what are we titrating? We are titrating a weak base. Ammonia is a weak base and we are titrating that with a strong acid. So what do you think? The pH should be above 7 because now, the pH should be below 7 because well, looks like it's different. What is given in the book? What am I missing or what am I thinking wrong? What?
Don't they have half the amount of acid? So there's only 0.1 the acid and there's 0.2.
But that would affect only the number of moles calculation. That shouldn't come into pH calculation. You know, I know. Let's just go ahead and make the table and do the calculation. So that, I'm trying to kind of predict, but if that doesn't work, then the hard way. Let's do the calculation. So, what do we have? We have HCl, which is 10 ml and 0.1 molar. So 0.1 moles per liter multiplied by 10 ml is 0.01 liters. So how many number of moles of HCl we have? 0.001, right? So that is moles of HCl. Now what is the number of moles of ammonia we have? 0.1 molar, 20 ml. So 0.1 moles per liter multiplied by 0.02 liters. How many moles of ammonia? 0.002 moles of ammonia. So this is what we have. And of course this reaction we have seen many times, so we can look up for the Ka value or Kb value. Okay, now let's see what is the reaction we are looking at. So we have ammonia, NH3 plus, we are adding H plus means, HCl means it's H plus, and what is it forming? NH4 plus, right? And of course, if instead of H plus, if you write it as H3O plus, then we can write water also there. But these are the species which we are going to focus on. Now, let's do the same table. Initially, how many moles of ammonia we have? 0.002 moles, no H plus, no ammonium ion. Then we are adding, so addition is 0.001 moles of H plus. So after the addition, what are we left with? Again 1:1 mole ratio. So from 0.002, 0.001 is used for the reaction. So what is left is 0.001, right? And no H plus. And how much ammonium ion will form? Same amount, 0.001. Now, we need, so this is the cation which is formed, and we are going to write the dissociation of this cation, right? Okay, so how does that dissociate? The opposite reaction. NH4 plus will dissociate as NH3NH plus, right? So NH4 plus dissociating to NH3 and H plus. So what is the Ka for this reaction? We have to maybe find out. It should be somewhere in chapter 16. I remember it was given in the table. So when we talked about weak acids or weak bases, let me keep looking. Strong acids, strong bases. Weak acids should be in the weak base. Or the Kb might be given. So if you have Kb, then you can calculate the Ka. Let's see. Ascorbic. Okay, here. Page number 691. Weak bases and their constants. So first one is ammonia. And Kb is given 1.8 into 10 to the power negative 5. So what should be Ka? How do we calculate? Ka equals Kw over Kb. Kb is what is given to us in the table. Kb is 1.8 into 10 to the power negative 5. So Ka should be 1 into 10 to the power negative 14 over 1.8 into 10 to the power negative 5. What do we get? What do we get, guys? What is the Ka value? No one is doing the calculation? Oh, 5.5 into 10 to the power negative 10. Okay, now go ahead and write the expression for Ka. So Ka expression is NH, concentration of NH3 over concentration of H plus divided by concentration of NH4 plus, which should be written as NH3 is 0.001, and this also becomes like H plus is the same as Ka, and NH4 plus is also 0.001 is equal to 5.5 into 10 to the power negative 10. So once again those two will go away. H plus is same as this. So pH should be negative log of the number 5.5 into 10 to the power negative 10. 9.26? Okay. No?
No, yeah, that's right. Now I have a question. Technically, what we found in the table are the number of moles, correct?
These are the number of, that is correct.
And we got away with it because we had something that canceled each other out, but when we
Yes, that is true. Good point, Jen. I completely missed that. These are the number of moles, and technically you should convert this into molarity back before we use in here.
And that's where we use the combined volume.
Yes, that is when you use the combined volume. Yes, I completely missed it. But since here we had both numbers, let's say for example, if you calculate the molarity, what you would do is 0.001 divided by what is the combined volume? 30 milliliters. So 0.03, right? What do we get there? 0.033. So technically you will be using 0.033 here and here also, right? And therefore it didn't make any difference. But yes, if the mole ratio is not 1:1, then we need to be careful because it may not be as simple as this. So good point. I also completely, forgot about that and got carried away. So, I know it's not always that easy, but good point. As long as it's 1:1, as you can see, it doesn't matter since denominator and numerator are going to get cancel each other. But if it's not 1:1, then we will be in trouble if we haven't converted into molarity. Okay, now that was only 17.7. I guess we are doing most of the time problems today, which I don't mind because that's what you need later. So let's do 17.8 also. Now here again we are calculating the pH, but now we are calculating the pH at the equivalence points. Right? Okay, so at the equivalent point, what is the calculation? That's what we are going to see. So we have again 50 milliliters of acetic acid, 0.1 molar and 1 molar NaOH. So we are going to assume at the equivalent point, both molarity of NaOH and CH3COOH are the same. Therefore, they will end up using equal volumes, right? So NaOH also will be, the volume will be 50 milliliters. Okay, let's see how the problem is worked out. So, number of moles of acetic acid is calculated using molarity times volume. And since we are looking at the equivalence point, it will take exactly the same volume of NaOH. Therefore, concentration of NaOH, wait a second, wait, okay. So it will take 50 ml of NaOH to reach the equivalence point. But at the equivalence points, what is the total volume of the solution? You had 50 ml acid, you added 50 ml of base to it. So the total volume has increased to 100 ml. And therefore, the molarity of the acetate ion formed is changed. It's not the same as CH3COOH concentration anymore. So you calculate the acetate ion concentration from moles of acetic acid divided by the total volume of the solution. Now, acetate ion is a weak base, so the base dissociation reaction, same as last time. Since it's a base, we are going to use the Kb value and substitute the numbers. When you substitute the numbers, you see that in the Kb expression, the only part missing is OH minus, or OH minus is the same as CH3COOH. And here we are going to make that assumption that negative X part, X is very small, so we will, remember those assumptions we used to make? So we will make that assumption, X is negligible, so we will just take acetate ion concentration as 0.05 and substitute that and you solve for OH minus. So if you get the OH minus concentration, you can calculate the POH, and if you know the POH, you can calculate the pH. So it's a little bit roundabout, but ultimately we will get there, right? Okay, let's do the practice exercise. This needs a little more, couple of extra steps from the previous one. So practice exercise is calculate the pH at the equivalence points when 40 ml benzoic acid and 0.5 molar NaOH. Okay, hit the screen. So, what is the concentration of benzoic acid we are starting with? 0.025 and we have 40 ml, right? So 0.025 moles per liter multiplied by 40 milliliters. That wouldn't work, does it? Point 0.04 liters. So how many moles we have? Benzoic acid? 0.001, that is C6H5COOH. So that is the number of moles of benzoic acid we are starting with. Now, just like in the previous problem, so we can assume that it's 1:1 mole ratio. So we can assume that this many moles of benzoate ion also will be formed, right? So the benzoate ion, which is C6H5COO minus ion, concentration also will be 0.001 moles. Remember, that is moles. Now, what would be the molarity of the benzoate ion? This is the number of moles, but what will be the total volume of the solution at the end of the equivalent points? What are we adding? 50 and 40? Okay, so if we are adding 50 and 40, no, wait a second. We are adding 40 ml benzoic acid. So at the equivalent points, you will be using 40 ml of NaOH. So the total volume will be 80 ml. So 0.001 moles divided by 80 milliliters is 0.08 liters. So what is the molarity? 11.25 into 10, 1 point. That's okay. I can erase 1. So 1.25 into 10 to the power negative 5. So that is the molarity of the acetate, not acetate, the benzoate ion. Okay. Now we are going to assume that benzoate ion is the weak base, so it will dissociate, and we already know the Ka value. So the benzoate ion is a weak base, so we are using the base dissociation constant. We need the Kb for that reaction. So the benzoate ion's Kb, how do we calculate? If we are given the Ka, the opposite of what we did in the previous problem. Previous problem we were given Kb, we wanted Ka, but here we have Ka, we want Kb. So what do? The Kw divided by whatever is given, which is the Ka. So let's get the Kb. Kb is 1 into 10 to the power negative 14 divided by Ka is 6.3 into 10 to the power negative 5. So what do we get? Yes. 10 to the power negative 5. Is that too small? You missed the decimal point? Okay. I didn't do the calculation, Iana. We trusted her, so we should beat her up. But no, that's fine. Actually, she's the only one who is sitting there and yelling at me on the numbers, so I'll go with that. That's okay. 0.0125. So that means 10 to the power negative 2. Okay, let us write it as 0.0125. That might be easy to use. Okay, so our KB value, we haven't got the KB value yet. What is that? Don't make the mistake this time, Jen. I'm trusting.
I know, that's why I keep
You are my backup plan, so.
It's 1.59 times 10 to the negative
1.59? 11 point.
10. 1.5.
Okay, 1.59 into 10 to the power negative 10. Okay, that is the KB. So now we can, just like the previous one, we can substitute things into KB expression. So we will again get, just like the previous example, we will get x squared divided by the concentration of benzoate ion, which is 0.0125 is equal to KB, which is 1.59 into 10 to the power negative 10. So solve for x. So x squared is, when you multiply those two numbers, what do we get? 1.59 into 10 to the power negative 10 multiplied by 0.0125. Am I doing some mistake, guys? Looks like that.
1.99 times 10 to the negative 12.
Yes, that is x squared. So we need the square root of that. .98 into 10 to the power negative 12. Uh-oh, something is wrong. Or I entered something wrong. I got syntax error on the calculator. So maybe I entered something wrong. What is it you guys get for x?
I got 1.41 times 10 to the negative 6, but I may be wrong.
1 point, that's what you got? Okay, if two people got the same, then I'll go with that. That is the value of x?
Yes.
Okay, now, so x represents what in our equation? It will represent the OH minus, right? So we need the negative log of that number. You guys go ahead and complete. So if you take the negative log of that number you just got, what do you get? 5.85. Now that is POH. So for the pH, we need to subtract that number from 14. Are we on the right track? 8.15. What are they showing? 2.1. Probably they might have round off things in between. If you have been, or they have been using just whatever number you get, you continue like answer, take the square root kind of thing. But if you are somewhere there, that is 8 point something, I'm good. Okay, I'm good with that. Don't worry about to the exact point. So I didn't finish that. So I think I must have entered something wrong format or whatever. Or maybe, okay, I think I did not. It was 10 to the power negative 12, right? When you calculated x squared, yeah, I didn't put negative. I think that's what it was. So they obviously could not do that big a number. I put as 10 to the power 12. It wasn't going to do it. So that's why it said error. Okay. Now I remember that. I didn't put the negative sign. Anyway, so that was the first part. We have one more. So the same one. We are titrating ammonia with HCl. Guys, I'll promise this time I will do the calculations properly. Okay? I mean, we will do together. Okay. So we have again 40 milliliters of 0.1 molar ammonia. Wow, it looks like we will just do these problems in this entire class. But that's okay. So 0.1 moles per liter multiplied by, how much is the volume? 40 milliliters. Similar to the previous one. So 0.04 liters. What is the number of moles? You already have the answer for this. Point 0.1 multiplied by 0.04. 0.004. Okay. So that is the moles of ammonia. Right? Now we are titrating that with 0.1 molar HCl. So we will have used 40 milliliters of HCl also. So remember, at the equivalence points, total volume is going to be 80 milliliters. Now, what is the reaction? So NH3 is titrated with H plus. So what is it we are getting? NH4 plus, the ammonium ion, right? So again 1:1 mole ratio. So if you have this many moles of NH3 titrated with H plus, the number of moles of NH4 formed also will be exactly the same. So we will have 0.004 moles of NH4 plus formed. Now we are not going to worry with the moles, but we need the molarity. What is the molarity of NH4 plus formed? Total volume is changed, so molarity is 0.004 divided by 40 ml plus 40 ml, 0.08 ml, liters, moles per liter. What do we get? 0.05. That is the molarity. Okay, so we have the molarity. Now we are titrating that with HCl. In the previous problem, okay. So this is the ion we are worried about. So at the equivalence points, this is the stuff present in the solution. So that NH4 plus is going to dissociate as NH4 plus forming NH3 and H plus, the backward reaction. We know the concentration of this stuff. We also know the concentration, no, we don't know the concentrations of these things, but we need the Ka value for this. Do we have the Ka value? In a previous problem, I think we calculated the Ka for NH4 plus. What was the Ka for this reaction? Something raised to the power 10 to the power negative 10. Look in the previous exercise. You calculated that already, Ka for that one. 5.5, yes. 5.5 into 10 to the power negative 10. Right, Jen? 5.55. Okay. I can make it 5.55. So 5.55 into 10 to the power negative 10 was the Ka. So if you substitute things into Ka, you get 5.55 into 10 to the power negative 10 is equal to, how do you write the Ka expression for this? NH3 is represented as X, H is represented as X. So when you multiply those two, you have X squared divided by NH4 plus 0.05. Right? That is the concentration of NH4 plus. Now go ahead and solve for X. So you should get X squared as, let me also do the calculation. Hopefully this time I won't make a mistake. Multiplied by 10 to the power negative 10. 2.775 into 10 to the power negative 11 is x squared. Is that what everyone getting? Okay. 2.77 into 10 to the power negative 11. Therefore, x is going to be the square root of that. .268 into, where is that? Let me write it. One, 2, 3, 4, 5, 6. 10 to the power negative 6. That is the value of x, right? So x represents h plus in our expression. So if you take the, so this is the same as h plus. So if you take the negative log of that number, we should get the pH. So pH is negative log of 5.268 into 10 to the power negative 6. Do we get the same answer as the book? 5.28. Huh. So that is the pH. Okay, so these two exercises, guys, I know it was a lot of things in there, but make sure you understand them. Okay? There will be sure short question from this. And definitely when I give homework also, I will make sure I will put maybe more than one problem of this sort so that you will get practice. Okay. Wow, we used almost an hour to finish those problems. That's good. So titration of a weak base with a strong acid. Didn't we do the problem? Titration of a weak base with a strong acid. The ammonia was a weak base titrated with a strong acid. So the pH at the equivalent point of this titration is going to be less than 7. Why? And usually methyl red is the indicator. Now let's try to make sense out of that. So when we titrated weak acids with a strong base, we said at the equivalence point you have the anion present. Anions are usually bases, therefore the pH is going to be above 7, right? Now the opposite case where you have a weak base with a strong acid, at the equivalence point what you have is the cation of the weak base. Like ammonia, the cation of the weak base ammonia is NH4 plus ion. Then cations are usually acidic. Remember that part from last chapter at the end? We learned anions are basic and cations are acidic. So cations are going to be acidic. So the pH is going to be always less than 7, slightly less than 7 at the equivalence point. That makes sense now? Okay. Now, so this part, remember when you do the weak acids, we will use phenolphthalein as the indicator because the solutions are going to be slightly basic. So the pH at the equivalence point, they will be somewhere around this range, not exactly at 7. So we use that as the indicator. Now here, when we do the opposite, that is weak base with a strong acid, we just said that the solutions are going to be slightly acidic. So we use methyl red, which has the range of just below 7, 6 to 4 as the indicator. Now how about polyprotic acids? Polyprotic acids means acids which have more than one acidic hydrogen, right? Now what you just have to understand this conceptually. I'm not going to make you do the calculations on polyprotic acids because that becomes really tough. And I don't think the book is also not, no, they are not giving us in this. I think it's beyond the scope of this course, doing the calculations on polyprotic acids. So it's just that you just have to understand that. So when one titrate a polyprotic acid with a base, there is an equivalence point for each dissociation. So let's say for example, if you take phosphoric acid, it has 3 different acidic hydrogens, right? So when first the base will completely normalize that first acidic hydrogen, whatever the amount, that will be your first equivalence point. But still you have 2 more. So you keep going, and we are not discussing about the indicators also in polyprotic acids. Polyprotic acid titrations have special indicators, because you can imagine there are 3 equivalence points which occurs in 3 different pHs. So you need something which will show at least 3 different type of color changes, right? So there are special indicators for polyprotic titrations. We will not be doing that, as I said. Just remember, they will have 3 different equivalence points. I mean, if it is phosphoric acid, let's say if it is sulfuric acid, then you will have how many? Sulfuric acid is H2SO4. So you should have 2. Exactly. How many acidic protons you have, that many equivalence points you should be observing. Okay, that takes us to solubility product. Let's consider the equilibrium between barium sulfate, solid, dissolved in water. Okay, now barium sulfate will not dissolve completely in water. So let's assume this is a saturated solution. That is just like your borax solutions today. I put barium sulfate in some water, and you've been shaking it for some time. Let's keep it for some time if you want. And so the maximum amount of the solid has been dissolved. That's what we are talking about. So if you look at that, this equilibrium, this is the expression, right? Solid, and when it is in equilibrium with its ions, which are Ba2 plus and SO4 2 minus ions. And if you write the equilibrium constant expression for that, you will get only BaSO4 and SO4 minus. Why we are not including the BaSO4? That is, look at the reaction one more time. This is the reaction. When you write the K, let's say I want to write the K expression for this. Equilibrium expression. How would I write it? Products, of course, I see products Ba2 plus concentration multiplied by SO4 2 minus concentration. Usually we will put denominator, the reactants, right? Now, why are we not using that in this case? Or should I use BaSO4 solid? No, why, Braden? You don't use liquids, solids and gases in, well, gases comes if you are talking about the partial pressure and all that, but at least we know that solids and liquids are not used in equilibrium expressions. So we will not use BaSO4. So the K expression will be just Ba2 plus multiplied by SO4 2 minus, right? Now when we talk about ionic solids, which is like this, dissolved, that K is called again with a special name. It is called KSP, or it is called solubility product of that particular ionic salt. So solubility product or KSP is the equilibrium constant for a particular ionic salt when that salt is in equilibrium with its ions in solution. Now please do not confuse KSP, which is the solubility product, with the solubility of something. Okay? When we say solubility of something, it's generally expressed as mass of the solute dissolved in 1 liter grams per liter, or 100 ml grams per ml, or moles per liter molarity. So that just solubility, when we just say solubility, means how much you had and how much water you used. That's all it means. Like 10 grams of sodium chloride if you had, and if you dissolve that in 1 liter of water, you can just write, oh, the solubility of sodium chloride solution I have is 10 grams per 1 liter. So it can vary from person to person based on how much solute you have used and how much volume you are using, right? Whereas solubility product is a unitless quantity, and that is again just like the equilibrium constant. It is a constant at a particular temperature. Now we can convert between solubility and KSP, and this table explains that. Let's say we have the solubility of something like Let's pick up NaCl. So let's say, as I said, 10 grams of NaCl in 1 liter. Okay? I know the solubility of the compound. Now, you can convert this grams of NaCl to moles of NaCl using the molar mass. Now, if you have the moles of NaCl, I don't know how many moles. NaCl is 35.5 plus sodium is what? 22.99. Okay. So it should be 55. But, well, let's take 55 for, we don't need the exact now. So let's say if you convert 10 grams of sodium chloride to 10 grams multiplied by 1 mole per 55 grams. So what do we get? How many moles we have? 10 divided by 55. 0.18. Now that is number of moles, and still I have 1 liter solution, or in other words, I have a 0.18 molar NaCl, right? Moles per liter is molarity. Now, this is NaCl we are talking about. So, NaCl dissociates, if 1 mole of NaCl dissociate, how many moles of Na we have? How many Na plus we have? How many moles of Cl minus we have? Just 1 mole dissociate, it is 1:1 mole ratio, right? So, if 0.18 molar NaCl dissociate, I will get 0.18 moles molar Na plus and 0.18 molar Cl minus, right? From the molecular formula, NaCl dissociates into Na plus and Cl minus. So, Ksp expression for NaCl will be what? Concentration of Na plus multiplied by concentration of Cl minus. We don't use NaCl solid in the bottom, right? Just the ions. So, Ksp will become 0.18 multiplied by 0.18. So, whatever that is the Ksp for this hypothetical problem. Sorry. I don't know what it. So, what do we get for the Ksp? 0.0324, or we can say 3.24 into 10 to the power negative 2. Now, I just want, just for curiosity, I just want to know what is the actual Ksp of NaCl. Do we have a table with Ksps? We should have somewhere. Come on, it's not in the book? I don't believe it. No, huh? You have it in the appendix? 1116. Okay. Do we have sodium chloride in there? No. Sodium. Well, because sodium chloride is pretty soluble. That is why usually, it's not given. As you look at the stuff which is given in this table, these are all mostly insoluble stuff, right? Because sodium chloride, since it is soluble, that is why such a small, such a big number here. But if you look at that appendix numbers, those are all very small because those are for the insoluble salts. Anyway, you got the idea. So if you know the solubility of something, you can convert to Ksp. Similarly, if you have the Ksp, you can do the backward reaction, right? So if it says it is the Ksp of NaCl, you can say, okay, NaCl is Na plus and Cl minus. So Na plus concentration should be half, not half, yes, half of the Ksp, and Cl minus should be half of the Ksp. Now NaCl 1 mole gives 1 mole each, so NaCl also should be the same number. If you know the molarity, you can convert that to number of moles. If you know the number of moles, you can convert that to grams using molar mass, just the backward calculation, right? So these two things are interchangeable. I think we have a calculation coming next. Yes, this one should be these two, that is Ksp, calculating Ksp from solubility, and next one might be calculating solubility from Ksp. So first one is the forward path we just looked at, calculating Ksp from solubility. Example given is solid silver chromate, and it is giving the equilibrium concentration of silver ion, and what is the Ksp of the product. So you need the equilibrium equation and the Ksp expression. Oh, it's an easy one. It's really easy. Let's do the practice exercise straight away. When you do this, you will see how easy this is. So, saturated solution of magnesium hydroxide in contact with undissolved solid is prepared. The pH of, oh, here the pH is given, okay. pH of the solution is found to be 10.17. Assuming that MgOH2 dissociate completely in water and there are no other simultaneous equilibria involving Mg2 plus or OH minus ions in the solution, calculate Ksp for this compound. Okay, so we have magnesium hydroxide, MgOH2 solid. How would it dissociate? What are the ions? Mg2 plus and 2OH minus, right? It is magnesium hydroxide, Mg is 2 plus, OH is 1 minus. So, okay, that is our expression. Now, if we have to write the Ksp, what would we write? We would write Mg2 plus concentration multiplied by OH minus concentration raised to the power 2, right? Okay. Now let's see what are we given. We are given the pH of the solution. So pH is given to us. pH is 10.17. So what is the pOH? 14 minus 10.17, which is, because when you write this, you are stuck. You need the concentration of one of these ions to proceed, right? And you look back to the problem and you see the concentrations are not given straight away. But when you see pH and an OH minus here, you should see, oh, okay, if I have pH, I can calculate pOH. From pOH, I can calculate the OH minus concentration, right? That is how you connect. So pOH is 3.83. Therefore, OH minus concentration, 10 to the power negative 3.83. What do we get? .48 into 10 to the power negative 4. Okay. So this is the concentration of OH minus in the solution. Okay. Now you have to think about this. Is that the same OH minus we are talking about? This is the total OH minus in the solution, right? Because pOH comes from the total OH minus available. Now in the Ksp expression, what do we have? It is raised to the power 2. Now the total OH minus concentration is this. Well, wait a second. No, you are right. So we need the Mg2 plus concentration. First, if you look at the way for calculating Mg2 plus, 1 Mg2 plus for every 2 OH minuses, right? So let's say in the solution, this is 2 OH minus, that concentration is 1.48 into 10 to the power negative 4. So what will be the concentration of 1 Mg2 plus? Half of that, which will be 7.40 times 10 to the power negative 5. Okay, so you know the concentrations of each stuff. Now you need to put the numbers into the KSP expression. So Mg2 plus is 7.40 into 10 to the power negative 5. And OH minus concentration is raised to the power 2. So 1.48 into 10 to the power negative 4 raised to the power 2. Solve that and that should be our answer. If not, we have to revise. Is that our answer? It is not the answer? Let me do it. I just started doing. What?
I got 1.6 times.
What do they have? What do you get? What did you get? So we have to square that part first. That's what I'm trying to do now. Well, if you got it, then I don't have to do it, right?
Yeah, the first time I forgot to put the
You've
negative 4 on it, so I just squared 1.48.
Oh, only you squared only 1.48.
One part squared, but not
Okay. Yeah, okay. So we got the answer? Wonderful. So that was 1.6 into 10 to the power negative 12. Good. So that is the KSP. Now the next problem, do you want to do the next problem also and finish today, or it's just the opposite process? Maybe it's good we just look at it right now so that your brain is connecting, right? So next is the KSP will be given to you. You want to know the solubility. So let's look at the example given. The KSP of calcium fluoride is given to you. Assuming that calcium fluoride dissociate completely and there are no other equilibria, calculate the solubility of calcium fluoride in grams per liter. That's what it is asking. So when you express solubility, remember you may have grams per liter, grams per milliliter, moles per liter. So whatever the question is asking, you have to express your answer like that. Okay, so here we are going to write the equilibrium expression again, CaF2 dissociating into Ca2 plus and 2F minus. Now here we need the table. Initially we have nothing and the change is mole ratio. So 1 mole of Ca2 plus, so plus X, but 2 moles of F minus, therefore plus 2X. And at equilibrium you have X moles of Ca2 plus and 2X moles of F minus. Now substitute those into KSP expression. So in KXP, remember, since the coefficient of F minus is 2, F minus is raised to the power 2, right? So X multiplied by 2X raised to the power 2. Jen will not make the mistake again. 2X raised to the power 2 is 4X squared multiplied by X is 4X cubed. So 4X cubed is KSP, therefore X is the third root of that number, which will give you the molarity of CaF2. But here the question was asking you what is the grams per liter. So you need to convert that moles to grams using the molar mass of CaF2. Easy enough? Let's try the next one, or the practice exercise. The KSP for LaF3 is 2 into 10 to the power negative 19 What is the solubility of LaF3? Okay, let me get the next screen. So first we need the equation. So LaF3, how does it dissociate? La3 plus and 3F minus. Okay, now if we have to write the KSP expression, what would we write? We would write La3 plus concentration multiplied by F minus raised to the power 3. Okay, now let's leave it right there. Now let's come back to our table thing. So LaF3, I'm writing it again, La3 plus 3F minus. Now initial we have nothing, and now we are going to write the change. Mole ratio, La will increase, every mole of this dissociate, La will increase by 1 mole, but what is the F minus change? It will be 3x, right? Because every mole of LaF3 will give 3 moles of F minus. So at equilibrium, La3 plus will be x and F minus will be 3x, correct? Okay, now let's substitute that into our KSP expression. So La3 plus, which is x, multiplied by F minus, which is 3x raised to the power 3. Okay, we have a big number here. So 3 raised to the power 3 is, okay, beat her up, Braden.
Yeah, I need to not talk.
27. Don't make that mistake. 3 raised to the power 3. 3 times 3 times 3. So 27 x to the power 4 is your KSP. Whose value is given? Right? KSP is given there. So 2 into 10 to the power negative 19. Now solve for x. That's all you need to do. So first would be just isolating the x term. So x to the power 4 is 2 into 10 to the power negative 19 divided by 27. What would you get? Two multiplied by, didn't put the 2 multiplied by 10 to the power negative 19 divided by 27 is 7.42 into 10 to the power negative 21. So x is going to be the 4th root of that number. So how do I do the 4th root in my calculator? Oh, I see it. So I need to put 4 first. Yes. 7.42 10 raised to the power negative 21. I get 0.00009281. So I can write that answer as 9.28 into 10 to the power 1, 2, 3, 4, 5, 6 negative 6. Is that our answer? Oh, they rounded off to 9 into, because the solubility product is given just with 1 significant digits. So if you round off that for 1 sig fix, it will be just 9 into 10 to the power negative 6. Right? And this is all in moles per liter. What if I had asked you to calculate that in grams per liter? What you would have done? What will be the next step? use the molar mass to convert the moles to grams. That is one extra step. So these calculations are easy, right? KSP ones? Okay, let's stop right here and we will finish the chapter in next class. Thank you guys. Have a